Hey, what's going on, guys? Commodore here. In this video I'd like to ask you a question. So what kind of software project would you consider if you know that you have only a few days left to live here on Earth, and then you will just die and that's it? So just a few words on the background of why am I asking this question to myself, basically. So we're currently having a war here in Ukraine. And if for some reason you've been following my chess programming channel, you could have even heard some distant explosions in the background while I was recording the video. But no, this video is not about like how horrible it is to live when it's the war around. It's not about this. It's about some core things to think about that you wouldn't otherwise be actually thinking of. So, when there was no war, I wasn't actually thinking about this, but now I do. And in this video I would actually like to share some of my recent projects that kind of answering the question, what would I do as a software project? What would I consider as the software project if I knew that I only had kind of a few days to live here, right? So without further ado, let's actually dive in. So first I'll demonstrate all the stuff. Not much there, and then at the very end I would like to talk a little bit why exactly I do consider this kind of projects. And then obviously I will ask you again, like, what would you consider? Because I'm really interested, like, what do you think about this? So some days ago, I finally created a chess program in 652 assembly. And the overall amount of bytes that it takes in the random access memory is only 909 bytes, so it's under 1K of RAM. It shares the structure that I've been working on like for years, basically, already at the moment. That's the good old maksymkorzh by emulator structure as presented in his tutorial on his website. So when I tidied up the code and actually re-implemented this in 652 assembly, eventually I had 717 bytes for the 652 assembly machine codes for routines, just the bare logic on, just to give the program an idea of how to play chess, basically. And 192 bytes for board representations, like chess rule encodings, so for all the variables. And again, like overall 909 bytes. So what is even more interesting that it initially, well, as far as this is under 1K, it's intended to be running on an unexpanded KM1, which has slightly more than 1K, slightly more than 1K RAM. And the initial version doesn't even assume that you're connected to the serial port, because by the time of writing this, I didn't actually have the serial mode in my online KM1 emulator. So let's get started by demonstrating this very initial version. So where is that actually? Oh, it's not this one. Yeah, this one. So here is the source code. Just quickly checking. I haven't been watching this. Okay, yeah. So this is the entire program. Yeah. Okay, so I actually want to grab the code from here. And copy. If only I can remember where should I. Yeah, it should be at 0. All right, yeah, obviously. So just grab this and go into the emulator, paste symbol, add 0, okay, upload. And now let's have a look at the hex dump. So from 0 to 300 should be fairly enough. So here we have the black pieces, here we have the black pawns, here we have the Y pawns and the Y pieces. Variables down below here represent some like piece move offsets, side to move, and some helper variables that are used along the way, like scores, etc. I've been covering this in the entire series on my chess programming channel, so for those interested, you can have a look at this there, at it there. So here we have the chessboard, the leftmost 64 scores, and here we have the p-score tables, which give an idea, which gives an engine an idea where to develop its pieces. So it tries to develop to the center generally. And here it's everything manual here. So if you want to make a move, you need to alter the random access memory. So for instance, to move a pawn. And also you need to make sure that you change the site. And the site is changed. If I could only remember where exactly the site has been changed. Site is changed at BC. Let me quickly check this. So 00 BC. Yeah, this is the site. But let's make computer actually play the first move. So in order to do this, I need to go to 0200 and click go, but it would be searching within depth 3, which takes a little bit too long. So I go to the next location, and here I can set up the search depth. So if I go in back to the address, to data mode, if I go to data mode and set this to 2, going back to addressing mode and 0200, and I click go. Now it searches, and it will find the best move, make this best move on board, and output the source square and the destination square on a display. So you'll now understand what exactly this means. So we just go to the hex dump again, and like this, you see, like it just moved the pawn from ABC from D2 to D4. It's not so bad, opening move, right? So just move the pawn. So the first letter, like the first digit, stands for row in this case. It's not really, it's not standard for chess, but it's really nice for this Q1 memory map. So 6, 0, 1, 2, 3, 4, 5, 6, and 3, 0, 1, 2, 3 goes to 4, 3. So actually, these are the actual board score indices, but since but because of this hexadecimal 88 board representation, it's really nice to have like the first letter as this was the row, this was the rank, and the second digit as this was the file. It's like not standard again, like, but anyway. So if I now stop here, and for instance I can go to 0200, I could have made a move, I could have shown you this, but well, I would better show you this in a version that plays in a serial monitor, because here it's not really that nice to show. So let's say I want to make, I want to see how engine is going to be playing itself. So I just can say go again and close this hex dump. You know, he would just now searching the move for black. So 1333. So let's have a look what is there. So 1333. 0, 1, 0, 1, 2, 3, and 2, 3, 3. So yeah, on D2, D4, it answers D75, and so on. If you just do this, go into hexadecimal to hundreds and press go all of the time, you will see how the engine is going to be playing itself until it actually draws. And it's obviously in under 1K. You don't have a threefold. You don't have the threefold repetition detection. But anyway, it plays chess, and adapt to it even doesn't blunder pieces in one move, so it's not that bad really. Okay, so hope it's clear. But then I realized that it's not actually that easy to play like this. Just to show you this, once. So if I want to make a move, assuming this kind of interface, then what I need to do, for instance, I want to play the knight G1 to C3, then I need to say 0, 1, 2, 3, 4, 5, 6, 7, 70, 1, 2, 3, 4, 5, 6, 76 goes to 54, 0, 1, 2, 3, to 55. 76 goes to 55. So for instance, if I go to 0076, we have a 90 here, data, erase, address 0055, data 0C, put a 9 here. Then for instance, again address 00BC. Okay, and here I need to change to black. So black to move is hexadecimal 10. Data 10 address, and before making a move, we can just verify the position to make sure that this kind of worked nicely. Everything is that I actually did push the knight as I wanted to. Let's have a look. Yeah, the knight was here, now the knight is here, so from G1 goes to F3. Yeah, so far so good. And yes, and now the engine should be searching for black actually. So if I go to 0200 and go, yeah, and it should now make a move for black. 01 to I guess it just developed the knight from B8 to C7, but let me actually make sure this is the case. Yes, indeed. So you see, like the knight moved from B8 to C6, not to C7, sorry, to C6. So B8 goes to C6. So we can play chess like this, and the engine can even check. Maybe if you set the depth, the search depth to 3, it would be seeing the mate in 1. In order to see the mate in more moves, well, since it takes ages anyway, assuming this implementation, I didn't use this. So it's not really for playing chess. It's rather for like proving the concept that chess can be written under 1K of RAM in 6502. And obviously, it's not like the best ever result or something. So Oscar Toledo, for instance, managed to create a chess in under 512 bytes, somewhere around 352. I might be wrong, but it's really miserable amount of bytes being used for this chess program. And well, actually that was written in x86 assembly, but anyway, that's much more tight version than this one I have here. So it's not really like something special. And there was chess like 1K chess for ZX Spectrum, for instance, and that chess, apart from chess playing program itself, also had like the graphical user interface, which took really a lot of bytes to get implemented. So yeah, nothing really special here so far. But you've already seen that it's not really that handy to play chess this way. And again, like even though it's not really for playing chess, you just go to like just download Stockfish and enjoy playing with the chess engine, right? Or go online and just play on Lichess. But anyways, this kind of issue of not being able to see the board gave me an idea that I actually need to add another feature to my Q1 emulator. And this is another what would I code if I knew that I would be living just a few days more, and that's it. So serial mode. This is the standard key monitor for serial mode. So here you can say, for instance, you can just enter the address, and here are the program bytes. Those have been assembled like right over in here. And exactly the same thing, you can change the bytes. So I would rather show you the next version of chess I made to give you an idea how this can be used, because the idea is really similar. So here I have chess TTY, which is it's already a little bit better, a little bit bigger. I think it goes slightly above 1K. Yeah, probably. We will now see this. It might be an issue on an expanded Q1 if we were talking about the real hardware, but on emulator works perfectly well. So copy. Let's update. Paste symbol. Yeah, you see like it goes about 1K, and that's because I just didn't want to take much time and effort in order to minimize the print board routine. So print board routine is really huge. Probably there is a way of making it smaller, but anyway, the rest is the gameplay is quite similar here still. So let me just recall. There should be print board. There should be an address that allows to print the board. I just forgot where, if I actually did provide that. I should have provided that really. Okay. Okay, TTY version. Okay, yeah, this is the address, 03F6. So, here, for instance, I could go to, yeah, well, first of all, it's not uploaded. So we need to upload this first, yeah. If I go to 03F6 and Shift G here, so like it prints me the board. So instead of going to the hex dump and using some cheating basically, because well, Kim1 doesn't have this hex dump like in a web interface, it's just the bare metal, right? So here in the serial mode, if we assume that this is the TTY emulator, sort of, we can already be printing to this like to the serial port. So I've been trying this thing like when I've been running a K1 emulator on Arduino and talking to that by serial port. So that's sort of an output that you would be seeing there. So here, for instance, what we have the board. So uppercase pieces are white pieces and lowercase are black. So rook, knight, bishop, queen, king, and pawns. 08 means that this is white to move. And then exactly the same. So if I go to here, one more, so depth, let's set the depth to 02 and I press dot key, okay, and make sure that it has been changed and go one back. So if I now say Shift G again, it's now searching, and once it found the best move, it actually prints the board and with a move that is already made. And notice that obviously engine changes the site just like in the previous version that I've been demonstrating. So yeah, let's make it like, let's ask it to make another move. So for instance, I can say 02 00 Shift G, and then I'll make a knight move again. Just okay. So now 00 1 2 3 4 5 6 70 1 2 3 4 5 6 76. Erase the knight, and then 0055 and 0C. Put the knight, and now to make sure that I did this properly, I already forget the address. 03F6, 03F6, and okay, so I moved the knight, but I forgot to change the site. So I'm going to 00BC. What? Nope. 00BC and 10. Okay, and 03F6. Okay, so now it's black turn. Now it's black to move. And let's ask make a move again. So it's a little bit better, right? So it's just a little bit better, but not perfect yet. So after this, well, before actually writing this program in 6502 assembly, I made a prototype in C. And by that time, I didn't even think that it's possible to compile the C code into 6502 for a K1 target, because the compiler I was aware of, the CC65, which supports a whole lot of targets like Commodore 64, Atari, and a whole lot of other platforms, NES for instance, but it didn't support Q1 until around 2 or 3 weeks ago, Dave Plummer, who's a retired operating system engineer from Microsoft, back from MS-DOS and Windows 95 days. He made this Q1 target for the CC65, and since then it starts being possible to compile the code. And since the version that is compiled from C takes it would be like 5K or even slightly more. First of all, because the compiler produces just a bigger code in this case compared to that I can do by hand. Probably it's only the case for this 65 compiler. I've been talking about distant explosions. This is one of them, yeah. So yeah, anyways, just to give you an idea, so if I have a look at my source folder, yeah, chess. Yeah, this is by the way. Yeah, so like the light will now probably turn up. Okay, hope at least I will leave until the end of this video. That would be nice already. Okay, so here is the source code. Here is the prototype for my chess, but it's just a test driver. So it doesn't actually have the part to play, the play loop, just the loop to play itself, just to test things, to make sure that the prototype outputs exactly the same move while searching as the assembly version. So I was doing this just to verify things, just to make sure that everything is working properly. But the plain version is this one. So I'm linking the new tab. So here is the plain version. It's already have this notation, a table of pointers for notations, so the user can add the moves like E2, E4, etc. And it has quite a significant main loop to actually play chess without a need to manually alter the positions and alter the random access memory to actually move the pieces and switch the side and all this and all the things. Also, it supports it calculates the distance to mate, and does it just yeah, it does plus minus, and also it promotes to queen, which the previous version didn't do. So it's a bit of an improvement, which is quite significant from the perspective of playing chess. Not that significant from perspective of programming it, but anyways. So I have a compiler version for this as well, probably somewhere here. Yes, this is it. Is this? Yeah, and this is already to be uploaded at 2000 hexadecimal, and this is this version is intended to be running the expanded Q1, the Q1 with a the target is known as the 60K extension. You don't need all. You obviously don't need all the 60K. You only need 6 or something. But anyways, it starts from 2000s, which is specific to the expanded camps. So we just update this stuff and paste it here. Assemble 0x 2000s now. So yeah, this is number of bytes. So this is pure compiler job here. So I didn't write these bytes. I just brought them to the format that the assembler can understand. Nothing special here really. So upload, and now I go to 2000s. Okay, and Shift G, and here we go. Code Monkey King 6502 chess. So enter your move. Now I can enter moves. I can say E2, E4. And I made a move, and now it asks me for a surge depth. And this is done, you know, like you remember, I've been manually switching the surge depth because I don't want the engine to surge forever. So I just say 2. I don't remember if I need to hit enter or not. Probably I don't. Maybe I do. No, I don't. Yeah, so it just makes a move, prints the score, prints the surge depth, prints the best move. So for instance, knight from G1 to F3. It doesn't have move validation, obviously. But anyways, okay. Distance explosion, guys. It's like this question, like, what would you like to write if you don't have much time to live? It's really on the cards. So I'm no jokes here, really. So yeah, unfortunately, this is happening, really. So yeah, plays another move, and so on. So I can say e5 takes on d4, for instance. Oh, that was wrong move. There is no e5. I should say e4 takes on d5. So yeah, now it would get messed up. But anyways, I just missed the move, so can't do much. Can you hear this, guys? Can you hear this? This is very unfortunate, really. Anyways, so I hope it's clear in regards to chess. And probably one last, yes, pretty last project for today to share with you. Is another one, also inspired by Dave Plummer, by the way. So this is the port of so-called Supermon Plus 64 version 1.2 that was originally intended to be running on Commodore 64. I just won't be like wasting your time demonstrating how this works on Commodore 64. If you know what is this, then there is no need for doing that. And I would rather demonstrate how this works on my emulator instead. So here I have this Super Kim Final, and this is at Supermon. So spend another few days on making this, and this is, by the way, it's written in assembly initially, but the building process was quite complicated, especially when I added this autocomplete for adding new address into assembly, which wasn't initially available. But yeah, I've been covering this on my chess programming channel for those interested in great details. Here I will just demonstrate the end result. That would be enough. So assemble and Xerox 9548 and upload. So as you can see, the downside of the current of the standard key monitor is you can't do much here. You can't even see the memory dump. You can only see the single address where it's available. So for instance, like here. But you have no idea what the bytes are all about. You can't disassemble them. If you want to put the program in, you need to assemble it by hand, so it doesn't have the built-in assembler. While this Supermon actually does. So without further ado, Supermon, Shift G. So first it prints the register state of the original Kim's register state after it encounters the break instruction. Obviously assuming that on load you've set up this 1C00 for non-maskable interrupt initialization for single step in and for break instruction as well. So these values are loaded when the emulator is loaded, because most likely that's something that you would like to do if you turn on your real Kim, right? If you want, because you want your device to stop when it encounters the break state anyway. All right. So this can be altered, but yeah, it's really more like for debugging. So how to demonstrate you this? So for instance, if I say go to like 300s, and obviously there is 0 at the 300s and just breaks there. So if I go back to 9548, then you see that in the little endian order we have the 0302, which is exactly like where the program counter kind of currently pointing to. So it's at 0302, it's about to be executing the next instruction, right? So for instance, what you can do here, you can inspect the memory. So we're starting from 0 page, but nothing really interesting there. So let's inspect the memory at, for instance, 200s. So here the Supermon holds the user input, for instance, which is, it's also really nice to see, like what the command that I've just typed here in the ASCII as the ASCII characters. It's really useful. You can alter whatever you want. So for instance, if if you go to like from 300s to, you can add the range, for instance, like this. So that's here. We can like add some code. So for instance, I can say at 300s, I want to say A9 and 10. This means load the immediate data of 10 to the A register. And see, like it just being there. You know, if I say G and 300s and go, then going back to 9548 and go, then you see that the A register now contains the value of 10, right? So it was 0 before, now it has the value of 10, and 0304 is where currently the program counter is pointing to. So hope it's clear in regards to the register. Same for Y, X, and Y register. If we do the function call and don't return, we'll have the stack pointer bin dropping downwards by 2 bytes, I guess. Yes, because that's the address. And if you have the some instructions that do affect the flags, like carry flag, zero flag, negative flag, then the status register, which encodes all the flags into the single byte, this would get affected as well. So I've already shown you how to inspect the memory, how to alter the memory manually. But one of the most kind of outrageous features of this is obviously assembler and disassembler. So if we go to 9548, so now I'm inspecting the memory of where this super monitor actually starts. But it doesn't make that big sense, because if you don't know the opcodes by heart, it's really hard to read what is written there. But you can do the following thing. You can say D and then 9548, and suddenly you have a disassembled version of all of these bytes that are kind of available up there. But what is even more cool, that you can also write the assembly code and get it assembled into bytes to the certain location in memory. So for instance, let's go back to M300s. So we have something there. We could write our assembly on top of this. It would replace this, but there is another another couple of cool features this super monitor has. So I just want to demonstrate you those. So first, before anything else, let me probably demonstrate the this transfer memory feature. So for instance, I want to bring this piece of code, say here. So I can say T, and then 300s, 301. I want to go to 318 and 319. So start, stop, initial start, initial stop, target stop, target start, target stop. Okay, and memory 30. Memory 30. Yeah, and we just got this values copied. But let's say we don't want this, and well, we could have erased just a few, but you can bulk erase, or it's better to say to bulk fill the memory with the F command. So say I want the range of 300s to 320, and I want to fill this with FFs and inspect the memory at 300s again. So like we got this FFs. Just to demonstrate, now obviously I can restore it back to zeros. So if I say, you don't hear this guy, but I already hear the ambulances going there, and probably the fire car as well. See, after these explosions, people are dying actually. It's really unfortunate. And the next day, this missile can land in this house where I'm currently at. So yeah. Enjoy your time with code like you can, right? Okay, so 300s, F, 300s to 320 and 00. So fill the memory with the zeros. M 300s. Yeah. Okay, so we just cleared the memory. Now the assembly itself. So let's write a simple program that takes the user input from the keyboard, echoes the character, and does this in the infinite loop. So sort of a type program. So I can say like A stands for assembly, and 300s, and now I want to say jump to subroutine. I just need to reference the address where I'm about to be jumping. I'm about to be jumping to subroutine. Get character 1E5A. So here I no longer need the little endian. I could just write as in the casual assembly. So 1E5A, right? And it assembles the line. Okay. And hold on a sec. I'm just a little wondering. Should have. Yeah, okay guys, so it's really good that I actually have two versions here. So the initial version didn't allow me to type the assembly for the next line, and I just tried doing this and it gave me an error because I didn't specify the next address. So I tried the next instruction without specifying the address. So that was a couple of days I spent to add a feature to actually autocomplete the address. It does this automatically on Commodore 64 because the address and the offset, like this address plus the number of bytes being encoded the previous iteration, so it would be 0303. It's stored into the keyboard buffer, which is in the memory location specific to the Commodore 64. And I believe that on the original Commodore 64, when you go to the next line, it kind of reads the buffer automatically and adds things to the input buffer automatically as well. That's just my assumption, but well, anyway, in the source code there was no kind of other places that could have just explicitly doing this, and hence it didn't work as expected on key one. So I've written my own custom. I can't even show you this. I've written my own custom. I call it autocomplete. We can call it autocomplete. There is a little piece of code. Essentially what it does, it just prints the carriage return, then the dot, and then it goes yeah, it loops over the input buffer. It actually loads through the keyboard. It loops over the keyboard buffer, so this X register is being incremented every time, and it stores whatever he found in the keyboard buffer. It stores to the input buffer, and then whatever in the input buffer is treated like something that you've just typed by hands. So there was quite sophisticated build logic for this. I just was compiling this from many separate parts. I have a whole lot of make files and link.py script to bring all this stuff together. You can have a look if you're interested. Nothing special here really, but here in the release I have this supermon plus key1 autocomplete. So yeah, this is the correct version. I don't know why I didn't pick up this the first time. I should have done so really, but anyways, so let's reload things, and I just paste this in and assemble 0x9548 and upload, and 9548 space shift G, and let's go again. So A300s, jump to subroutine 1E5A, I guess. 1E5A, yes. And now it prints this dot, which means that in the keyboard buffer, I can even show you this keyboard buffer if you're interested. So the keyboard buffer is right over in here, and it already contains the next address. Unfortunately, my built-in hex monitor doesn't provide the ASCII representation like this one. But if I try to show you here, it would just override this the input. I won't be able to demonstrate the feature itself. So what it did now, so it did take this part, and put it here, and then whatever I would be typing now would be overriding this. Okay, so for instance, here I want to say jump to subroutine, and I want to echo the character that I've just typed. So output character 1E0A, so 1E0A, and it assembles the second line. What a fantastic thing, right? Now I want to go do this in the infinite loop, so I just want to jump to 0300, and it automatically notice that it automatically converts the address to the little endian order, so we have 0003 instead of 00300, because that's how the 6502 CPU deals with addresses. All right, so enter one more time to escape from the assembly mode, and now we can disassemble at 300s, for instance. So what we got here, right? So we got this jump subroutine to get the character, jump subroutine to echo the character, and jump back to 300s to do this in the infinite loop. Now what we can do, we can say G, which stands for go, and the address where to jump. And now I can say, hello YouTube, hope you like the video. So this is kind of it. I can't stop the program from within the program, because it's just an infinite loop. So in order to stop the program, I need just to trigger this kind of interrupt on the by pressing the stop button, basically, and I drop back to the original Kim's monitor. But anyway, I hope I kind of managed to deliver the sort of an atmosphere of what I personally treat to be an absolutely important thing. And like I said, if I knew that I'm about to die, like very, very soon, then this sort of work is definitely something that I would have considered doing, because it means so a lot to me, and it makes a whole big sense to me, as opposed to this kind of modern business applications like web scraping, like a whole lot of things that you can get paid for, but unfortunately it doesn't make any sense, well, at least for me personally. So with this kind of things in mind that I've just demonstrated, you guys, really wondering, what do you think? How would you answer the question? So what would you like? What would you write as a software project if you know that you don't have a lot of time to leave further on? So it's important that you don't have, like, I don't know, half a year to write a compiler or something big. So if you have very few time and you really need to make something small, then what would it be? Please let me know in the commentary. This is from my side. Thanks for watching. Until next time, and take care.